analytics services within Rockwell Automation. What we're going to kind of talk about today is how you take the data that presumably exists on your plant floor and elevate it and turn it into useful outcomes, essentially focused around the analytics and monitoring capabilities that we can deliver as a managed service to you. So we're going to do a little bit of just kind of talking about what is that digital footprint, why is it important to leverage it, an overview of monitoring and analytics services, what we can do in total within my portfolio, and then we're really going to focus on the back half around what we call predictive maintenance as a service. So being able to deliver predictive maintenance outcomes to you, predicting failures before they actually occur on your equipment. We'll have a couple of use case demonstrations. I've managed to wrap this up a couple of minutes before the end of time, so if you have questions that you want to save for the end, we should be able to do that. Otherwise, if you've got something in the flow of the conversation, feel free to jump in, ask it. If need be, we can, I might defer it because the topic's coming up in some slides or whatnot, but I'll get you guys out on time. I know I'm standing between you guys and a beverage or three, so we'll kind of go through it. So leveraging the digital footprint, there's all sorts of kind of outcomes that you can achieve with kind of that digital space, right? Having data on your plant floor, you can do different things to drive down cost, improve operations. The one we're primarily focusing on from a monitoring and analytics service standpoint is around that total machine downtime. One of the priorities our customers typically have is to keep machines up and running. You can't really optimize a machine that's broken all the time or is choking your process or whatever. So we're really focused on making sure those assets are up and running, and if they're not up and running, shortening the cycle it takes to go from down back to up. So that's what we're delivering as part of the service, and it requires that digital floor to enable it. So one of the things we've found is more and more customers are starting to have data available. They've instrumented, they're collecting data, they have it sitting in a historian, but they're not really taking action on it. They're not getting proactive with the data. More often than not, they've got an operations person or a maintenance manager that kind of looks at the data every once in a while and kind of goes, huh, that's interesting, that's nice, okay, maybe we need to tweak this or do that, but they're not really getting proactive with that information. Now where we're kind of going with the IIoT space is that we can now, in a shared service model, we can now access that data, provide our engineering capabilities and tool set on top of that data to deliver outcomes to you that you might not be able to deliver from yourself, either from an investment standpoint, a resource standpoint, or both, quite frankly. So the data is presumably there, but the key is only a quarter of our customers are really doing anything with it, and if they are doing something with it, they're running on basic tools, they're building something from scratch when there's access to all sorts of capabilities out there. So we really want to connect to the data and bring those outcomes to the customers as a managed service. So kind of lay the land, analytics is probably one of the most abused words in the English language right now. So kind of want to provide context of what analytics means in this industrial automation space. So we kind of have a scaled view. This is a Gartner model that we're leveraging and really looking at the left-hand side. The basic analytics are typically delivered at the edge or by the customers themselves around that basic subject matter expertise of those assets. The advanced analytics are where you're leveraging technologies and tools more frequently to deliver those outcomes. To kind of give you an idea of what each one of those boxes really means, we're going to use the analogy of a car. I'm presuming everyone drives a car. A descriptive analytic in that analogy is your speedometer. It tells you the speed you're going. It doesn't tell you whether you're going to get yelled at as people pass you by 20 miles an hour faster than you are, or if you're going to get pulled over because you're doing 30 miles over the speed limit. It just tells you what you're doing. Still requires you to make a decision around what that is. The diagnostic, how many of you had a check engine light come on? That is a diagnostic analytic. It's telling you there is something wrong, but it's not necessarily giving you the content. If you're like most people, you ignore it for 3 weeks, you finally take it in, the mechanic puts an OBD link in, pulls the error code, and then charges you $400 for the privilege of diagnosing your error. But that check engine light is a diagnostic. It's giving you some sort of indicator of a fault, but no real context around it. Torturing this metaphor a little bit more, where you get into the predictive in that car would be your fuel's going to run out. Hey, you got to go fill up. You got 30 miles left on that tank. It's looking at what your average consumption is, how much you have in the tank, and it's doing a calculation to predict when that fuel tank's going to run out. So that's going to be a predictive. It tells you what's going to happen, but it also doesn't tell you what you should do about it, or what to do about it, or how you do something about it. Where we get into prescriptive, that's where not only are we predicting an event, but we're now doing something about it. So to take that fuel gauge to the furthest extent, not only could it predict that you're going to run out of fuel in 30 miles, it could also link to your navigation and tell you, hey, there's gas stations here, 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 and here, across the next 5 miles where you could go fill up. So it's now giving you a solution to the problem that analytic has found. And that's how it's getting prescriptive. So what we're going to talk about in kind of the context of the managed services we're delivering, from a monitoring standpoint, we're really delivering that descriptive diagnostic standpoint at an enterprise and plant level, so that everyone's looking at those same basic analytics in the same way. When we get into the predictive maintenance as a service, that's where we're delivering as a service that predictive and prescriptive analytic outcome around those critical machine assets that you might have. Any questions on that before I get too far down the road? Okay, good. Either you guys are all asleep, or the head nodding means you're in agreement. So I'll take the latter. So when we look at remote monitoring and analytic services in general, we really have four major we don't really call them offerings, but four major outcomes we're delivering. The first one being application monitoring as part of a support package, where we're making engineers available to your application. They understand your application, but we're also able to remotely monitor that. We're building dashboards, KPIs, reports, trending, status indicators, those types of things. We're building it in the cloud so that your operators, your executives, your plant manager are all looking at the same information around the various assets on the plant that you're monitoring. So we're doing that at an application level, looking at it in total across all those smart assets. Similar in concept, we're doing what we call infrastructure management. We've called it network monitoring in the past. What it really is it's delivering to the OT space an IT monitoring solution, where we're monitoring network switches, server capacity, servers themselves. Again, we're tying out and providing alerts and alarms if you're exceeding your CPU capacity, if you have a network switch that's dropping packets, excuse me. So we're monitoring and supporting those network and server assets on your plant floor, again, to maintain that OT network, to keep your processes up and running. Drive monitoring is kind of a focused flavor of application monitoring, where we've built specific dashboards and alerts and alarms around various models of Rockwell Automation drives. The goal being, we've got support engineers that are experts on those drives, that are sitting in a command center, looking at the screens, waiting for alarms to trigger, and then are proactively calling out to customers to say, hey, we're seeing this fault, let's troubleshoot how to resolve it, get it fixed, and move on. So we're supporting those drives remotely. It reduces the requirement for the customers themselves to have that technical knowledge about how to troubleshoot some of those drives. They're getting very complex, and they're in very critical applications, so any downtime is expensive. So it's keeping those drives up and running, because typically, at least half of the issues we've seen with drives are sympathetic to the overall application. It's not an issue with the drive itself. So helping manage and troubleshoot where that issue lies is of value to customers. And then predictive maintenance as a service, and we're going to go into great detail on this in the back half of the presentation. In a nutshell, we're delivering machine learning technology with supported engineer capability to build out predictions that we can deliver to customers around their critical assets to say, hey, you're gonna see this issue pop up, you got a bearing that's gonna fail in a month, you know, take action on it, or hey, this machine is operating abnormally from what we've seen in the past, you may want to inspect and go do something. So we'll get into greater detail on that. This is where we kind of get a little bit more technical on this, so we've kind of highlighted what we're doing. This is just a quick slide to talk about how we're doing it and kind of give you some guidance on what the value proposition is around this monitoring and analytics service. So on the left side is an overview of the architecture, the how we deliver application monitoring, predictive maintenance as a service, alarm management and support. On the right is a similar graphic, but it's specific to the infrastructure management, those networks and servers. Same concepts, but because of the nature of the case, if you will, I don't want to say application, the nature of the situation, we use slightly different technologies in both cases, but the concept remains. You've got data sources at the plant floor that we connect to via a gateway. We bring the data from the gateway on the plant floor up into the cloud, where we've got a number, we based on Microsoft Azure, and then we've built a number of applications and services in the cloud layer to deliver the green boxes or the green border for our customers. So the goal is that the customer is providing the data sources and then ultimately receiving the outcome without having to manage any of this technical stack, keep it up to date, build it on their own. We're delivering that as part of the service model. If you saw this picture 3 months ago, it would look different. If you saw this picture 6 months from now, it'll look different. The technology is evolving and changing continuously. That's part of the value we're bringing, is managing and rolling that technical debt, keeping up with the technology so we can continue to deliver these outcomes to the customer. So you don't have to worry about the how, you just worry about the what. One other note in this architecture, we have a green box around managing assets remotely. We've purposely built a remote access capability that can exist on the same hardware box, but is separate and isolated. So we do have that, the effect of a secure data transport capability that is separate from our secure remote access capability. Again, to try and keep those isolated, keep bad actors from being able to use our remote access or data transport applications to come back inside your four walls. So we've purposely built with security in mind. We're backed by Microsoft security technologies as well. So that's part of what we're managing, is that security posture around the capabilities as well. Any questions on this? Comments, concerns? Everyone still with me? Okay, good. All right, so that's kind of the how in general. Now we're going to get into kind of the real nerd stuff around predictive maintenance as a service. So what are we delivering when we say predictive maintenance as a service? What are we delivering? We're not actually really inventing anything new. Predictive maintenance capabilities have existed for a number of years, but we certainly didn't invent the as a service model. But what we're doing is we're taking technology that's proven, reliable, machine learning and predictive technology, and we're building it in a cloud environment with our engineering support wrapped around it, so that we're actually doing the development and the deployment and the management and maintenance of those predictive alerts, so that the customers just consume alerts and analysis as an outcome around their assets. They don't have to spend any time in the software developing capabilities. They don't have to go build models. They don't have to go re-engineer things. We're delivering that as part of the service model. So we're collecting and storing data. We're running it through the machine learning technology. Our engineers are providing guidance and context around those alerts that are being reported, and the customer is simply consuming those outcomes for themselves. So they can focus on, all right, I've got a problem, how do I fix it? As opposed to, how do I build this thing that shows me there's a problem, right? So that's where it's different and unique, is that as a service model, delivering both the engineering and the technology. So kind of in practice, how does this look once we're deployed at a customer location? So the left side of the dashed line is kind of on-premise on the plant floor. You've got a typically mechanical asset or application that's sitting on the floor, that's instrumented. It's feeding its data to some sort of data collection, whether it's a PLC, historian, database of some sort. We connect via the gateway to that data source or data sources. We can build and connect to just about any data capability out there, and that will only expand with the recent partnership with announced Monday with PTC. They have Kepware OPC, as part of their technology and capabilities, so we'll start to leverage that even more than we already are to build native connectors to data sources. But that gateway is doing that data collection, passing it up into the cloud. In the cloud, we've deployed the predictive maintenance technology, and what our engineers are doing is gathering that data, and they're building those predictive models, setting up alerts around, and we'll get into more detail around what that alert looks like and what's responding to it. But they're building those predictions, and then when those predictive models see a data pattern, because really in practice what we're really doing is saying, I'm looking for a specific data pattern. If I see that data pattern, send an alert. And then we've got the context of what kind of alert is it? Is it an anomaly, meaning that we know what normal is and this is not normal, so somebody has to figure out what's going on, whether this is good or bad or indifferent, or an event where we've got a specific pattern associated with a failure or a quality issue or something else, where that alert is saying, yo, this is broke, we gotta go fix it, right? So those alerts get sent to both the Rockwell engineering team and the customer expert on site, and then the engineering team will work with the customer to provide that context around the alert. And we'll see a few more details on it, but they'll talk about, hey, these are the sensors that we see associated with this prediction. This is, we've got a 80% probability. This has been happening on and off. Maybe the pressure's going up, the temperature's going down. Provide the context for that alert, whether it's an anomaly or an event itself. The customer then engages as necessary, feeds the information back to us around what happened, and then we go maintain or deploy new agents potentially as a result of whatever came of the directed action on the asset. Okay, so that's a day in the life of what this service looks like. People kind of go, oh, well, this is great. I want 100 of these. I'll deploy it on everything. I'll take it all. And that's where we have to have a bit of a, well, let's slow down here. This does not replace standard traditional maintenance strategies. There's a spectrum of maintenance strategies that make sense. Break fix, preventative maintenance, predictive maintenance, that's all part of a spectrum that serves the plant floor. For predictive maintenance, an ideal deployment really consists of four things. You've got to have a critical asset. What defines a critical asset? It's really important. It's really costly if I'm down. Or it stops production. It chokes my process if that asset's not up and running continuously. That's what defines a critical asset. If you've got an asset that fails, once every 6 months and it's a $5 fix and it costs you $100 of downtime, predictive maintenance doesn't make sense. It's a great capability, but it's also not inexpensive, right? So having that critical asset, typically we're looking in the range of anything north of $200K a year in annual downtime cost. That makes sense to deploy predictive maintenance. We can get that ROI pretty quickly on that. Data, it's got to be instrumented. I had a potential customer ask me, oh, we want to put predictive maintenance on these assets. Okay, what sensors do you have? We don't have any. It's a 40-year-old, 500 horsepower motor. I can't predict on literally nothing. So you gotta have data, it's gotta be there. Preferably, we want historical data so we can start to build predictions before we deploy. But at a minimum, we just need at least 5 data points around the asset or application we're trying to predict on. It gives us enough meat, if you will, to feel confident to be able to build at least a normal data pattern so we know what normal is for the asset. Preferred is event and maintenance history, right? So we can build predictions as we go, but if we have historical data and we have historic event data around particular failures or maintenance activities or quality issues or whatever, we can take that data and build predictions around those. So from day one, we have agents deployed to predict those events. If we don't have it, it's not going to be mission critical, but at a minimum, we need to have a context around that asset. What could be an issue, what could fail, so we can build out the capability. And then lastly, we've got to have that connectivity, right? Because we're doing this in the cloud. This software can be deployed on-prem, but that's not where we're going to be able to scale efficiently. We can't deliver the engineering support on each local instance. So an on-premise deployment would be a traditional model where it's training, you're getting trained on how to use it, which means your engineers are delivering the outcomes as opposed to us delivering them. So we're focused on a connected cloud-based solution. And we do require the customer to have some subject matter expertise around their assets. Had a potential customer in a big plant, lots of cost around downtime. When you started talking, what data do you have? What do these assets do? They said, I don't know, we got 2 guys that run around the plant floor and fix anything that's broken, and we can't spare them to talk to you because they got to go around and fix stuff that's broken. Well, we can't necessarily predict in a vacuum. We don't know every single, industrial automation asset that's ever existed and be able to build predictions without any context. So having that expertise is critical. So this is just a quick view at kind of what ideally everything would be required in the required column that you see up here. But we kind of broke it down as what is absolutely the minimum viable set of information we need versus what's nice to have. And really the difference between required, preferred, and optional is how quickly we can get value to you. How quickly can we roll out? Can we have predictions on day one versus building predictions as we go, right? So the big thing is, and I've kind of talked about it already, we need to have the data, information, subject matter expertise, connected, real-time data streaming in. Once we build predictions on data sets, we still need to have that real data coming through because the system's got to watch. And it's looking for those patterns we've trained on, and as soon as it sees that pattern show up, it's going to trigger alert. So we got to have that real-time data flowing through. So, pause there. Any questions or comments before we get to the kind of the couple of use cases? This is kind of the real interesting things where we see the practical application of this capability. Okay. Either people are dreaming about the beverages, or I'm just doing an amazing job in walking through this. So I'm going to walk through 2 specific use cases. This one in particular was a compressor station with a history of bearing failures. We had a customer, and this is a case where we used historic data. So we knew about the bearing failure. At the time we were analyzing the data. Basically what it comes down to is this is a very large, expensive piece of equipment. It's basically, this is for an oil and gas pipeline company pumping millions of gallons of oil down the pipeline every day. In fact, the industry generally, but this customer specifically, they have a 99.5% uptime ratio. So they're only down about 0.5% every year. Any guesses as to the annual cost of that 0.5% downtime? This is the audience participation. Any guess? $2 million? No. That was one incident. Good. Way to read ahead though. I appreciate that. Good job. $3 billion a year in 0.5% of downtime. So if you can shave off 0.1% of downtime, that's a significant. I don't want to do the math live, but it's a significant, opportunity. In this particular case, they had a catastrophic bearing failure that resulted in $3 million in loss. It was a combination of damage to the equipment, downtime around that event, lost work. This event, this bearing failure actually occurred 19 days after they had taken the asset offline for 9 days to do a routine maintenance schedule. So they had swapped out a bunch of components, updated, took it offline for that, and that's attributed into the $3 million loss. If they had known about the bearing issue and had fixed it during that downtime event, the planned maintenance, they wouldn't have incurred this issue. So it was a pretty significant issue, and we happened to be talking to them at the time. This happened, I think, a month or two before we really started talking to them in earnest, and they said, okay, you're kind of talking a big game. We've got this 14 months of data around this asset. Can you put your money where your mouth is and show us that you could have predicted this bearing failure? They had a vibration system in place, but I'm not exaggerating. It gave them about a half a second notice before the bearing, basically not exploded, but shredded, came apart in pieces. So the goal was find the bearing failure, validate and prove it as successful. So just to kind of walk you through the machine learning environments, unless you're really into stuff and want to spend a lot of time with it, it's not great for live demonstration. So we're going to really kind of narrate through it in a series of screen grabs of the solution. This is kind of one of the main views. We're going to walk you through kind of what this view means, and then that'll give you the context as we walk through how did we build a prediction. So this top swim lane is the sensor data itself. So in this case, we've just plotted all 32 data tags into this environment. It's going from I want to say it's like May of 2015 out until November of 2016, and it's all unitless. It's just plotted out there. We can do stuff like doing removing high and low stuff, or anything data that's unnecessary. We can clean it up a little bit. But we're really just saying, this is the data we want to plot. This next row, this is operational state. All we're doing is telling us the environment one of three things. Either the machine's on, which means the row's blank, the machine's off, which means it's white, or that it's a failure, or it's a training event, whether it's a failure or a normal, and that's where we're indicating red. So we're simply saying, the equipment was in a failed state at this point between the fall maintenance and the bearing failure. That's what we've identified. So it's one of three states. This swim lane is identifying the probability. So if we've got a pattern that we're looking at, this is just simply saying what's the probability that we found a match, or, and that's the case of event, and the inverse of we've got a normal, it's telling us the probability that we've got a data pattern that's new or unknown. So in this case, we're saying, hey, we're looking for a prediction here at the end where the catastrophic is. We see a pattern here. We're seeing a little bit, and this is plotting all the data, no context. We haven't done any cleanup. We see a little blurb of something there, but we're not there yet. And then this last one is the data conditions. So it's around the data itself. And again, we're just giving three indications. We're either saying that it's good data, which means it's green, it's bad data, meaning it's black, or it's training data, or it's essentially representing this represents the pattern we're looking for. Okay, so that gives you a little context. Some more application context. So there were 4 downtime events that the customer knew about: fall maintenance in 2015, spring maintenance in 2016, fall maintenance in 2016, and then the failure. Bear in mind, this whole narrative we're walking through, this took a matter of a couple of days. Importing the data, doing some initial analysis, talking to the customer. Okay, so our goal is to find the bearing failure. So we switch to, we're actually looking for anomalies in this case, but we started to do our analysis. So we said, all right, before the fall maintenance and that bearing failure, let's treat between the spring and the fall maintenance as good normal data. We're saying whatever the data that's there, those patterns are associated with normal operations. And what we're trying to look for is red indications that the pattern here, right before the bearing failure, is substantially different than what we think is good. Is there any red there? No. All the red's over here. So at first glance, that tells us, all right, well, maybe this isn't good data. Maybe the bearing failure was occurring way out here, so this isn't good data. So we said, all right, let's switch to before the year ago, before for their fall maintenance in 2015. And again, treat that data as good. We're looking for red out here. We don't see it. We see it again here. All right, so something during this fall and between the fall and the spring maintenance activities, something was substantially different in operation, but not different than the actual bearing failure. So at first glance, this says, oh man, the bearing was failing all the way out here. We don't understand. So we dig in to the actual data, and that's where we discovered that there was a temperature sensor, and at first we thought it was a faulty sensor, but there was a temperature sensor around the bearing. And it was, we could see the data, you can't see, we don't have it plotted, called out specifically, but the temperature sensor was reporting slowly day over day, the temperature in the bearing started to go down, and then it flatlined and was continuously low by about 20 to 30 degrees over a 6-month time period. Okay, now the temperature lowered itself, or lowered gradually, so operators didn't notice it. And they're also not looking at each individual parameter and necessarily trained to know that bearing temperature. They're looking for spikes, or significant quick acting sags, and they're not looking for a gradual decline and then flatline. So if you have any mechanical engineering experience, or you've ever worked on a car, the temperature being 30 degrees lower than normal is not good. Lower temperature, higher viscosity, higher friction. So that's actually the root cause of that bearing failure, is the bearing was overheating for a time of over 6 months, right? It was getting substantial mechanical wear because there was more friction going on than there should have been. So the damage is already done, which is why we're not able to detect a failure event. So then we worked with the customer to dig in and said, okay, why would that temperature sensor go down? What's the context? And we provided that context to them and said, hey, this is what we're seeing. What they came back and what it turned out is the way the cooling system for the bearing works, there's 2 pipes, one that goes directly to the bearing that the oil flows through, and one that goes through a chiller and then goes into the bearing chamber to cool it. And the system's set to modulate how much goes through which leg to keep it at a constant temperature. And there's a valve that sits at the first juncture of those 2 pipes, and that valve regulates how much they flow through the chiller versus the straight line to keep it at a constant temperature. Turned out that valve was failing over time, and eventually failed all the way to the point where it was stuck open, so all the oil was flowing through the chiller and going into the bearing. They replaced that valve during their routine spring maintenance because somebody noticed it had failed, but as a result, it had been running over 6 months in a failed state. So right there is a prediction we could build to say, hey, we would have noticed that valve. We have an alert we could have deployed around that valve, identifying it. When that temperature slowly decreased, it would have identified as, hey, this is a new pattern. Now, if they had changed the setting, we simply would have triggered an alert to say, hey, the pattern's different, and somebody would have said, oh yeah, Joe changed the temperature setting, that's what it's supposed to be. Okay, great, we'll retrain the agent and ignore that. In this case, we would have picked up an anomaly, would have noticed the valve issue, they would have done an inspection, replaced the valve, and prevented the bearing failure. But the task at hand was predicting a bearing failure. So with that context, we eliminated all the data between the fall maintenance and the spring maintenance because we know it's not good. So we're just looking at prior to the fall data of 2015, after the spring data of 2016, including some after the fall maintenance in 2016. Now, if you remember the image before, we just had a little red here and a little blurb down here. Now we're seeing at least a week out, a greater than 90% probability of a failure around that bearing. We're also starting to see indications out here. They're not strong or consistent, but we're starting to see it. But now, keep in mind, we're also looking at all 32 data parameters. Those data parameters may not be relevant. The humidity sensor on one end of the machine may have no relevancy to the bearing. So then we look at all the data tags that we have, and we see, well, even the one that's the differential pressure, the one that's most contributing to this failure prediction is less than 5% correlation. So we say, all right, we need to do some refinement. We're going to eliminate some of these sensors from our analysis in this particular case and see if we can get a better prediction. So in this case, we ended up narrowing it down to 4 specific parameters. And now what we find is all the way out in March, a 90% correlation to that failure. So we would have triggered an alert out in March of 2016 ahead of that failure. They could have even done an inspection during their spring maintenance that bearing was in failure. Now, traditionally, we'd like to see this more consistent, but given the fact that we're operating off of data, that the bearing is already failing at this point, so we don't have a great data pattern to build off of. We don't have a true normal to work off of. This is probably about as good as we can get. Now, if they had, in this case, they had additional compressor stations of a similar make and model that also had data, we could go back and, presuming one of those assets was operating normally, we could build a normal based on that data set and apply it to this information and refine this predictive agent even further. Okay, but again, bear in mind, the customer is giving us context around the asset, they're giving us the data, we're building all of these predictions and the context and feeding it to the customer. Questions on that? Okay, moving on to the next use case. So this is a customer with heavy rotational assets, so a spinning core, and this core, wears out, needs to be replaced. Sometimes they do it on a routine basis. Sometimes that core, when they pull it out, is worn and was the right time to replace. Sometimes they pull it out and it looks brand new. So they're wasting downtime, wasting replacement efforts. So they wanted to determine, hey, when do we really need to replace this core, and how long can we go before we need to do it? So same kind of familiar setup. We've got 7 months worth of operational data, 20 parameters. This is right here is where the core is replaced. This is the very first pass looking at all 20. We've got a prediction about 10 days in advance of when that core would need to be replaced. But now we're going to work and saying, hey, can we make that better? Can we get it further out? Can we be more accurate? So this is kind of giving you the context of what we're building out. This is 4 different views, or 4 different, essentially, data sets that we're using to build predictions. And it's a little hard to see, on the screen up here. But this is the one we just looked at, where it's all sensors. If we reduce the sensor suite that we're using to either all the wear sensors or just the lubrication sensors, we can move the prediction out at least 5 days. And then if we move it, if we eliminate it or reduce the model down to simply 3 critical wear sensors, again, this is trial and error, we're doing some context from the engineer, we can get that up to at least a 17-day prediction on when that that's rotating cylinder needs to be replaced. So that provides context. Now, with consulting with the customer, we're refining this further. So this is kind of a zoomed up view, and we can create different levels of alerts and alarming around those predictions so that we can make sure we're giving the right amount of sensitivity to the customer. So in this case, we've set the condition at 50% probability, so we've got a 50% threshold that the pattern we're seeing is the failure pattern, and that we're seeing that pattern continuously for 24 hours. And what you see in this top row is when an alert would have gone off. The red kind of indicators means that's an alert that would have gone out. You can see that we're out a week and a half in this situation, somewhat continuous alarming situation, but that doesn't, because we're kind of low, maybe that's not what the customer wants, right? They're not certain they need to replace it. So we, in this case, said, all right, well, let's bump it up to 85% for probability and continuous for 24 hours. We reduce, we get pretty precise, but we also sacrifice time, right? So we're looking at an alert going out 5 or 6 days in advance of the need to replace. versus maybe 12 or 13. So we then talked it through and said, all right, 85% probability, but continuous for 4 hours. So we've reduced the amount of time that we need to see an alert. Now we've got a very consistent alert, and it's out about 10 days, which the customer said that's the right amount of time we need to plan our maintenance activity to yank that cylinder out and put in a new one. So we are playing with the tool set to get the right outcome to the customer based on their evaluation of what they need and how do they need it. So how does these, when we're sending out these alerts and notifications, what does that look and feel like? Basically, you've got the alert that triggers. It can be a text message, it can be an email. In fact, I don't have my phone, but I just got one today I got an email on an alert for a customer today. And an email goes out, we'll see a screenshot of it, give some context around it, and then our engineers will do some analysis and engage the customer to say, hey, we saw the alert, this is what we're seeing, these are some guidance we can give you around what the problem is, and then the customer takes that and does their intervention. If it's an anomaly, they're going to typically inspect, see if there's anything going on. If they find something, fix it. If it's an event, assuming they know what the event, and this is getting into prescriptive, they know how to solve the problem, they'll go do that. And either way, they report, kind of come back to us and say, hey, this is what we did, this is what we found. You know, that alert was crap, it didn't give us anything, there was nothing wrong. Okay, then we need to go retrain the agent. Or hey, we saw the event, or we found a new thing, we need to be able to predict on that in the future, go build a new agent. So this is a screen grab of what an agent, like a text or email comes with. You get some tag data, we get some statistical analysis, you get some screen grabs that we can provide, but that event's gonna go out to you and our engineering team. We're going to react and respond. We'll maybe bring the customer into the machine learning environment so they can see the trends and the visualization for themselves. But we're going to acknowledge that alert in the application and then stand by to take further action based on the customer feedback. I talked about anomalies and alert and events. This is just kind of providing context of how those discussions go when we do get an alert. The anomaly alert, it's more about, hey, here's the context of what we're seeing. This is the system within the application where we're seeing the alert. You might want to go look at your cooling system or your filtration system or the bearing or whatever, right? This is where we're seeing the alert take place, versus the event where we've built an agent, in this case, to look for this O-ring failure. And we're giving the context of what that failure is and the probability. The customer goes, inspects, says, yep, it's confirmed it's a failure. We're going to replace that O-ring at the next planned downtime, and then we're going to refine the alert further as necessary. So this is kind of that information sharing and investigation. Again, we're interacting with the customer, building better and better agents with each iteration and discussion. The customer kind of provides the context as we provide these alerts and notifications, whether an anomaly or event. The customer is giving us the context of, is this alert low risk, moderate risk, high risk, right? And that's defined as, if it's high risk, I gotta get this machine stopped, do some real-time intervention to keep this from being some sort of failure or whatever. Versus a moderate risk, whereas, all right, I know what I've got to build this into my maintenance schedule when I have my next planned downtime and build it out. Or low risk that, hey, we're either fine, it's no issue, or it's something we can take up whenever we have an issue, right? So the customer is providing this context, and we're building it into the alerts and alarms that we issue around those events going forward. So this is kind of just capturing how do we close this out, right? So if we get an alert or alarm, we're going to really take three directions. Either it's a new operating state, that's a new normal, it's acceptable, or we found a new fault, we need to address it. Maybe we create a new failure agent, or it's unknown, it's unresolved, and we need to resolve it as we get more context. Once we know what we're in, we can go out and build new agents, retrain the existing agents. If we find that, well, it was just a bad prediction or a bad alert, we'll retrain the agent so that doesn't happen, and then we deploy as the customer requests it. So with that, I got about 4 minutes left. So any questions or comments around this topic? Any thoughts? Useful, not useful, boring, super boring? Anything? It was just so well delivered that you captured it all. Or it's 5:45 on in the Pacific time and you're all exhausted. I think I'm gonna go with the latter.
4 minutes from beer.
Yeah, that is true. 4 minutes for sure from beverages. So, all right. Well, if there's no questions here or in the Facebook Live feed, then we can wrap it up. We'll let you guys get out a couple of minutes early. I appreciate it. One last request for those in the room: go to the